Hi everyone, our topic is inferring user profile information on social media. So why are we inferring social media profiles in the first place? Well, here are just a list of some motivation. So there's increasing popularity, advertisements, recommendation systems, scoped content sharing, as well as understanding homophily in communities. So this is a summary of the paper that we went over. It goes over a data set of Rice undergraduate and graduate student profile pictures, and it uses attributes such as college, major, year, department, and school. It will then use a community detection algorithm in order to find these clusters, and then from there, it will use these formed communities in order to predict the user attributes specified before. And now we'll talk a little bit more about the actual detection algorithms.
Existing algorithms for community detection start with the seed node and greedily add neighbors until a strong community is found. Cosset's algorithm chooses neighbors that maximize the ratio of intra-community edges to intercommunity edges for the nodes that are on the outskirts of the community. Bagor's algorithm adds nodes with the lowest outwardness. Outwardness is the number of neighbors outside of the community minus the number of the neighbors inside and is normalized by degree. Law et al.'s algorithm is the same as Cosset, but the metric is based on all of the nodes in the community.
The new proposed metric is normalized conductance. I won't go into too much detail, but just know that it focuses more on the success of a single community rather than the whole structure that modularity does. In addition, it can be compared among different graphs of different sizes and shapes. And just a way to actually read the metric is in a range from -1 to 1, 1 being best, -1 being the worst, and 0 being comparable to a normal graph or a random graph.
The algorithm for local community detection uses a greedy approach to try to maximize the normalized conductance. The input is a graph G and a subset of users S in a community. The output is the other members of that community. First, the graph is divided into two components, A and B, where A is equal to S. Then select user V and B that will generate the highest increase in normalized conductance for A when it's added to A. Step 2 is repeated until there's no user in B that will increase the normalized conductance for A, and A is then returned.
So it turns out that for expected attributes, they are actually able to predict at pretty high accuracy the correct information given only 20% of the data. So this implies that community detection can be used to infer data about members of the community. And if you look to the right, you'll notice that for the undergraduate students, the major was not easily predicted, but for the graduate students, the year was not easily predicted. So obviously, this method still has a few flaws, but it still shows that homophily to a certain extent does exist among members of a single cluster. Now, some problems to be addressed with this current algorithm. So right now, a greedy approach only is efficient for static networks, since it would have to be rerun every time a new vector or edge is added. However, we all know that social networks are constantly changing, so there's a need for a more dynamic algorithm. In addition, overlapping communities are not accounted for, so a node or person will only belong to one community or the other. And lastly, the algorithm has not explored directed edges, which is more relevant to platforms such as Twitter and Instagram, in which there is a follow and followee relationship. And next, we'll go on to the dynamic side of the algorithm. Our dynamic solution is based off this existing algorithm, structural clustering algorithm for networks, otherwise known as SCAN. So this essentially creates neighborhoods based off a similarity metric that's determined by how many neighbors are shared by each member in the community. And here's some terms that you can look at, and then we'll move on to a quick demo. So this is a demo of dbScan, which is a variant of scan. But as you can see, it starts from a singular node and then finds all of the nodes next to it that share a lot of different neighbors. And then it'll move on to the next one. You'll see they're colored different colors, but you'll also notice that there's outliers that don't fit in the community because they do not share neighbors. And yeah, that's just a quick little demo. So essentially the way dynamic scan works is it will execute the scan algorithm on the first run through, but on every subsequent run it will update clusters based on which edges have been changed. So as you can see, we set x as the first node of the edge and x prime being the opposite node. And if x is a core, meaning it reached the threshold for its epsilon neighborhood, then we propagate the ID of x, meaning we create a cluster from x, if the IDs are all similar. And then if the edge was removed, then x prime is no longer directly reachable from x. Then we propagate the ID of x prime so that that creates its own cluster. And then otherwise, it will be an outlier or a hub. Next, if x is not a core, if it used to be a core, then for all neighbors of x, if the IDs used to be similar and the neighbors were unchanged, we'll propagate the ID of x prime. If x was not changed, then it will make x a hub or outlier, and for all neighbors of x that are not a core or neighbors of a core, we'll make the neighbor a hub or outlier. So next we're going to move on to a little analysis of the algorithm. So, according to the graphs, dynamic scan actually performs faster community detection on dynamic networks than scan, and it maintains the same kind of modularity measurement as scan does. It also has inclusions of hubs and outliers, which can affect the modularity, but encompasses a more realistic view on communities. And these can, if you take a look at the graph on the top right, you'll notice that it operates better on most cases, but sometimes it'll spike a little bit above scan. And this is because during those intervals, there are greater changes. So we concluded that dscan will operate better when iterating across smaller changes and ran more often than not. And now we'll move on to another proposed algorithm, Aslam.
The order statistics local optimization method is another community detection algorithm. It can be used on graphs with directed edges, weighted edges, overlapping communities, hierarchical communities, and dynamic communities, as opposed to other methods that are limited to undirected graphs. It locally optimizes the statistical significance of the clusters, and this is the probability of finding the cluster in a random null model. The algorithm uses cluster analysis to optimize the statistical significance metric. Single cluster analysis optimizes the metric for one cluster. It first looks at adding external vertices to the subgraph, and then prunes non-significant internal vertices from the subgraph. Network analysis uses single cluster analysis to look at the entire network. It starts at a random vertex I, and the first cluster C is equal to I. From the neighbors of the cluster, Q most statistically significant vertices are added to C. Single cluster analysis is then performed, and this entire procedure is repeated, starting from several vertices to look at different graph regions, and this then yields a final set of clusters that may overlap. OSLOM is a three-phase algorithm. It first looks for significant clusters until it converges. It tries to detect internal structure of the resulting set of clusters or possible unions, and then it detects hierarchical structure of the resulting set of clusters. OSLOM performs well on directed graphs. It also accurately detects any overlapping communities, and it can recognize the absence of community structure and the presence of a random graph. However, it may return less accurate results in some cases because it finds homeless vertices when the communities are fuzzy. And the running time is dominated by an exhaustive search of significant vertices, although a greedy approach could possibly be used. So, for large networks, it could be used as a refinement technique.
So, in conclusion, after reading these three papers, we realized that user profiles can indeed be predicted using community detection algorithms, and they can be further improved by using more versatile algorithms such as dscan and oslam, which perform just as well but can satisfy different needs and situations. And by continuing to expand on community detection, we believe that user profile prediction can continuously also be improved.